Hello everyone and welcome back. So I had a galactite ask me why it is we see different constellations from different places, and oh boy, that is actually a very long answer, so I decided to make a whole video about it, so let's go. Now this is actually surprisingly complicated, or maybe I'm just outing myself as easily confused, but in any case, we're gonna go through it step by step. So starting from the simplest case, let's go ahead and consider this to be our Earth, and then we'll make ourselves a little observer. I really cannot draw. Okay, so we have our Earth, we have our observer, not to scale, obviously, and then we need to consider that there's basically a celestial sphere of stars all around the Earth. Now these are going to be fixed throughout this entire discussion. They are not going to move at all, so you can kind of think of them as like the walls of the room. Those stars are also infinitely far away in this approximation, and we can consider them to be marked on the grid that's very similar to latitude and longitude, except it's called declination or dec and right ascension or RA. Okay, let's give our Earth some poles. We'll say that this is the North Pole. And then obviously on the opposite side is going to be the South Pole. And then right around the middle we have the equator. Should I probably have done this before I started recording? Yes. Can I draw a straight line? No. Okay, now just like the Earth has an equator, our celestial sphere also has an equator, which is called the celestial equator, and it is even with the Earth's equator, and then the north and south poles are kind of even with the celestial poles. Because this reference system for the celestial sphere is relative just to the Earth, which will be important as we go. So if our observer is on the North Pole, and she looks up at the sky, she's going to be able to see half of the sky, right? Because the Earth itself is going to be blocking the other half. So she can basically see kind of 180 degrees from horizon to horizon, and then all 360 degrees around her, and that's going to be half of the celestial sphere. Now you may be thinking the Earth is curved, so she should be able to see more than half because she can see past the curvature of the Earth. But remember, this is not to scale at all. The observer's height relative to the horizon is actually very, very small and basically completely negligible. I mean, I'm 6'4", and if I was standing up, I would see maybe 0.04% more of the sky than if I was just lying down flat on the ground. In fact, there is a bigger effect from the Earth's atmosphere because it refracts light. So near the horizon, the refraction actually causes us to be able to see a little bit below the horizon by about half a degree. Now we're basically going to be ignoring this when it comes to the stars and the celestial sphere, but it will come back into play later. Okay, so our observer on the North Pole, she can see half the sky. Now say we have an observer on the South Pole, they are also going to be able to see half the sky, but it's just going to be the other half of the sky. Now as our observer moves down in latitude from the poles towards the equator, they still only see half the sky, but what they start to see is that this half of the sky they can see here overlaps with the half of the sky you can see at the same latitude on the other hemisphere. I should have got something to like block so you could see at different latitudes. Can we jerry-rig something together? So now our observer is now at a latitude that is not at the pole, but if you kind of put their perspective up, you would see that they can see, right, this half of the sky if you projected this outward. But of course, we are actually going to be staying in this frame of reference where the North Pole is up. So an observer at 40 degrees north latitude can see as far down as a -50 declination. And then since you can see 180 degrees over, that goes up to +130. But declination, like latitude, doesn't get any higher than 90, which is at the pole. So what actually happens is that you can see past the pole another 40 degrees to +40 on the other side. This means that our observer can see all of the right ascensions at +40 dec and above. All right, let's add in our first complication because we know that the Earth is rotating, so that's obviously going to affect what our observers can see. Now at the poles, it doesn't have any effect because even though they're rotating, they're still only seeing that same half of the sky. The locations of things in the sky is moving, but which part of the sky they can see is not, and obviously the same is true on the southern hemisphere. Now let's consider instead an equatorial observer. Now they can see this half of the sky from +90 to -90 and then 180 degrees of right ascension. Now as they start to turn, over the course of 12 hours, they can see the entire sky. Now that might give you pause because you might be thinking, shouldn't they need 24 hours to see the entire sky? But that's not the case. And in fact, I spent way too long trying to make sure that this was the case by holding out my arms and spinning in a room and making sure I could see things. Anyway, but think of it this way. So consider when they start over here, this is their eastern horizon, and then over here is their western horizon. And as it starts to turn, they're seeing more and more of the right ascension over here until after only 180 degrees of rotation, which is 12 hours, now their eastern horizon is right over here where they started the western horizon, so they have in fact gone through all 360 degrees of right ascension, and so in the next 12 hours they're just going to be seeing more of that. For the observers in between, they're kind of going to see a combination of these effects. So at the declinations above their corresponding latitude, they're going to see all 360 degrees of right ascension all the time. And down here at their very minimum declination, you can see as they spin out an entire 360 degrees rotation, that one point will spin all the way around, so they will eventually see all 360 degrees of right ascension for that minimum declination. And then at 0 dec, it's actually going to be the same as the equator, so they will see all 360 degrees of right ascension after only 12 hours. Now, you may have noted that I'm talking about 24 hours, and of course, we don't see the stars for 24 hours of the day. Now, this isn't because these stars disappear, because remember, we said the celestial sphere is fixed, it's unmoving, but what happens is the nearest star to us, the sun, is so bright that it washes out all the other stars and we can't see them. So basically, whenever the sun is up, we can't see the stars. So we'll consider the sun being up for 12 hours and down for 12 hours, and we're going to make the assumption that it is instantly dark as soon as the center of the sun is below horizon and vice versa. Now for our polar observers, of course, this isn't going to have an effect. They're still going to see their same half of the sky, but just for half of the amount of time. An equatorial observer is still going to see the entire sky because remember, it only takes 12 hours for them to see all 360 degrees of right ascension, but they're not going to see as much of it. So for these things that are on the horizon, they're only going to see them for an instant. And for our observers in between, again, it's going to be a combination. So they're still going to see all 360 degrees of right ascension all the time for declinations above their corresponding latitude. And down to 0 dec, they're still going to eventually see all 360 degrees of right ascension as the Earth rotates. Now, however, this point of their minimum declination, they're only going to see 180 degrees of right ascension because it's just going to become part of the daytime the rest of the time. And in between 0 dec and the minimum declination, that will vary accordingly. Now let's go back to that assumption we made about it getting instantly dark when the sun goes below the horizon. Of course, we know from our own personal experience that dusk and dawn exist. Now, dusk and dawn are both considered twilight officially, and there's actually 3 kinds of twilight. There's civil twilight, nautical twilight, and astronomical twilight. Now, during civil twilight, the sky is still pretty bright. You can maybe see some bright stars and bright planets, but not very much of the rest of the stars. And this starts and ends when the center of the sun is 6 degrees below the horizon. Now, in nautical twilight, the sky is much darker and you can see a large variety of stars, but the sky isn't totally dark and you can still kind of tell the difference between the sky and the horizon. Lastly, there's astronomical twilight. Now, during astronomical twilight, the sky is basically going to be perceived as being fully dark. If you were trying to study some more fainter objects like diffuse galaxies or something, then you might run into issues, but in general, walking out, you would consider it to be fully dark. And this starts and ends when the center of the sun is 18 degrees below the horizon. Now, since what we're talking about here is just walking out and looking at the stars and the constellations, I think that astronomical twilight can be considered part of the nighttime, but I will consider both civil and nautical twilight to be part of the daytime. I think you could kind of make an argument either way for nautical twilight, but that's just what I've chosen to do. Now, because that starts and ends 12 degrees below the horizon, if the sun is over the horizon for 180 degrees of its arc, now we kind of have to consider it as being 204 degrees. And that's not all, because the sun is not a star, it's not a single point of light, it has some sort of a width on the sky. Now, the width of the sun is about half a degree, but this goes back to that atmospheric refraction we were talking about. So we can actually see the sun for a little bit longer when it goes beneath the horizon. So we need to account for around a degree roughly on either side to account for the width of the sun and the refraction. So let's consider how this restricted field of view is going to affect our observers. Now, for our polar observers, we already know it's not going to have any effect. The next easiest one to consider is probably our equatorial observer. And now, instead of being able to see all 360 degrees of right ascension, they basically aren't going to be able to see for 13 degrees on either side of the sun, which means that they're only going to be able to see 334 degrees of right ascension, which is roughly 93% of the sky. Likewise, our observer at a different latitude is only going to be able to see 334 degrees of right ascension at 0 declination. And down at the minimum declination they can see, instead of seeing 180 degrees, they're now going to see 154 degrees. So basically, for a 12-hour night, an observer is going to be able to see 50% of the sky at the pole, up to about 93% of the sky at the equator, and it's going to be somewhat in between at different latitudes. So we already know for our polar observers which 50% of the sky they're going to see, because it's the same 50% they've been seeing this whole time. But for everyone in between, the question becomes, which part of the sky are they seeing? And that answer depends on the time of the year. See, throughout the course of the year, the sun is going to black out different parts of the celestial sphere. Now, of course, we know that in physical space, the Earth is orbiting around the sun, but remember, we're considering a reference frame here that is centered on the Earth. So say during March, the sun is over on this side of the Earth. Now, by definition, at the March equinox, the sun has a right ascension of 0 degrees and a declination of 0 degrees. This is called the first point of Aries, and it's actually located in the constellation of Pisces in the modern day. Now, this is because of the precession of the Earth's axis, but that happens on much longer timescales than what we're discussing here today, so that's all I will say about that. So if the sun is over at 0 degrees right ascension, then the portion of the sky that our observers are going to be able to see is going to be centered over at 180 degrees of right ascension. So at 0 declination, or at the equator for all declinations, our observer will be able to see from the right ascension of 13 degrees all the way around to 347 degrees. And right at this minimum declination, it would be all the way around from 103 degrees all the way over to 257 degrees. Now for an observer at 40 degrees north latitude, this would mean they would be able to see as far south as parts of the southern constellations of Puppis, Vela, Centaurus, Lupus, Norma, and Ara. On the other hand, an observer at 40 degrees south latitude would be able to see as far north as parts of the constellations of Lynx, Ursa Major, Canis Venaticis, Bodes, and Hercules. So if the sun is over here during March, it'll be over here during September, right? Because that's 6 months later. And by definition, at that September equinox, the sun has a declination of 0 and a right ascension of 180 degrees or 12 hours. Side note, right ascension is usually measured in hours and minutes, which is 24 hours is the same as 360 degrees, but it doesn't really matter. You can convert between them, and I think maybe it's a little bit more intuitive to think about it as degrees. Now that point for the sun at the September equinox is called the first point of Libra, and it is located in the constellation Virgo in the present day. And basically we get the exact same thing, but now on the other side. So our observers can now see centered on 0 degrees of right ascension. So at 0 dec, that's from 193 degrees of right ascension all the way around to 167, and it would decrease down to 283 degrees over to 77 degrees. So for our 40 degrees south observer, they would be seeing constellations as far north as parts of Cygnus, Lacerta, Cassiopeia, Andromeda, and Perseus. And for our 40 degrees north observer, they could see as far south as parts of the constellations of Telescopium, Indus, Grus, Phoenix, Eridanus, Horologium, and Pictor, and I definitely should have practiced pronouncing these before I did this. So, it was pretty complicated, but we got there in the end. No, we didn't. See, because so far we've been speaking about the sun being above the horizon for 12 hours and below for 12 hours, and that only happens on the equinoxes, which is why I chose the equinoxes as the examples we were using, or at the equator all year round. Now why is it? That's because the Earth is tilted relative to its orbit around the sun. But remember, we're using a reference frame that's centered on the Earth, so the Earth isn't tilted in this reference frame. North is straight up. But what that means is that the sun does not have a declination of 0 all year round. Its declination actually changes as it moves through the celestial sphere. Change in declination then is limited by the amount that the Earth is tilted, which happens to be around 23.5 degrees. So the sun can have a declination as high as plus 23.5, which happens on the June solstice, or as low as minus 23.5, which happens on the December solstice. Now we saw before that an object's declination kind of dictates how long it's above the horizon, and this is true for the sun as well, which means that throughout the year, the sun is above the horizon for varying amounts of time. So when the sun has a positive declination, it is spending more time above the horizon in the northern hemisphere, so that's from March to September, and when it has a negative declination, it's spending more time above the horizon in the southern hemisphere, so that's from September to March. And this is why we have seasons. Okay, so how does all this affect what our observers can see in the night sky? Now for our equatorial observers, it doesn't. They always are seeing the sun 12 hours above the horizon, 12 hours below, so they're always seeing that 334 degrees of right ascension like we talked about. But let's consider our 40 degrees north latitude observer and say it's the summer solstice. So now the sun has a declination of plus 23.5 and a right ascension of 90 degrees. Now the amount of time that an object is in the sky depending on its declination at a given latitude is not a linear relationship. By that I mean at 40 degrees latitude, 23.5 declination is about 82% of the way between objects that are up for 0 hours and objects that are up for 24 hours. But the amount of time that an object at 23.5 is up is not 82% of 24 hours. That was a mouthful, but I hope it made sense. Luckily, there is an equation we can use to calculate this depending on the angles involved, which are the declination of the object and the latitude of the observer. Now this does depend on both angles, so let's hold one of them fixed. So let's say 40 degrees latitude for your observer. As the declination of the object changes, this is how the time in the sky or above the horizon changes based on its declination. And we can see that it bottoms out at 0 hours and it maxes out at 24 hours because obviously it can't be less or more than those. And actually this equation is symmetric, so if we held the declination of an object fixed at 40 degrees, the amount of time it would be in the horizon, depending on the observer's latitude, would basically look the same. Okay, so using that, we know that the sun is going to be in the sky for just under 15 hours when it is at plus 23.5 for 40 degrees north latitude. That means of the 360 degrees that the Earth is rotating, 223 degrees will have the sun above the horizon. And then remember, we have to add on the effects of the twilights and the width of the sun. So it's actually more like 249 degrees. Now, as you can imagine, since that means that the night is a lot shorter, our 40 degrees north observer is going to see a lot less of the sky. At their minimum declination of minus 50, they're only going to be able to see between 214.5 degrees right ascension and 325.5 degrees of right ascension. And at 0 dec, they'll only be able to see between 124.5 and 55.5 degrees. This is parts of Lupus, Norma, Era, Telescopium, and Indus. Now likewise, at the December solstice, the sun is at a right angle of 270 degrees or 18 hours and a declination of minus 23.5. We can use our equation to calculate that means the sun will be above the horizon for 9 hours and 8 minutes for an observer at 40 degrees north latitude. Meaning that once you take into account all of those extra effects, of the 360 degrees of the Earth's rotation, 163 of them are going to be during the daytime. Now note that this is not symmetric with the summer solstice, and that's because of these effects we've been talking about with the sun, and so they act to make the day longer, so it's not symmetric between the solstices. So now with this longer night, our 40 degrees north observer can actually see more of the sky. So they can see all 360 degrees of right ascension down to less than 0 dec. And down at minus 50 dec, they can see all the way from 171.5 degrees to 8.5 degrees of right ascension. And of course, you could do a similar calculation for the southern hemisphere. If all of that left your head spinning, I totally understand, because I actually literally tried while trying to get this all down on paper for you, and I'm still not 100% sure that I got it all actually correct. But what I think is really important here is just understanding the why of this, the mechanics of what's happening and why we see different parts of the sky throughout the year. But when it comes to the practicality of actually understanding what you are going to see at your location at a given time, I highly recommend using one of the many tools out there that's available to do that calculation for you. Now back in the day, that might have been a paper planisphere. I actually used to have one of those, long lost, unfortunately. But nowadays, of course, there are many apps and websites where you can do this. But hopefully you understand at least a little bit better the main factors that contribute to why we see different things in the sky based on the Earth's rotation, its orbit around the sun, and its axial tilt. So the range of declinations that you can see is basically dependent on the latitude that you're observing from, while the range of right ascensions that you can see depends on both the declination and then also the time of year and the time of night. And of course, what you can actually see in the sky on any given day is very heavily dependent on light pollution where you are, objects obstructing the sky where you are, and unfortunately the luck of the weather, which any astronomer will tell you often does not like to cooperate. So thanks for watching. Cheers! I'll see you again next time.